Right. Waveguide equation becomes exactly like the Schrödinger equation. Right. So we'll cover the waveguide equation. Like this. So waveguide equation for photon. Schrödinger equation is for electron, and waveguide equation is for photons. It starts from the Maxwell's equation. We have four Maxwell's equations in a dielectric medium. The first one is divergence D is equal to rho, which is the free charge density. And in a dielectric medium, free charge density is 0. So we have divergence D is equal to 0, and that is divergence of epsilon times E becomes 0. Epsilon is a susceptibility of a medium, dielectric medium. D is related to electric field with epsilon 0, 1 plus chi. And this becomes epsilon 0 n square E. This can be derived from the simple harmonic model for the dielectric medium, where the absorption coefficient is 0, the susceptibility, so the chi becomes n square, 1 plus chi becomes n square, which is the refractive index. And H is just 1 over mu 0 B. So we just have the four Maxwell's equation in terms of electric field and magnetic field B, like this. So second equation is Faraday's law, and the third one is Ampere's law with the 0 free current. So we have called B equals to mu 0 epsilon round E over round T. And we need to derive the wave equation, and wave equation starts by taking curl of equation 3. So by taking curl of equation 3, we have curl of E is equal to curl of B, and curl of B can be replaced with equation 4. So we have we can remove the B. So we have a second order unmixed, uncoupled differential equation like this. Curl of E is equal to 1 over n square over c square round square E over round T square. So this is the vector wave equation. And vector wave equation can be converted to the scalar wave equation, and the condition is when this one, divergence of epsilon times E is 0, that is gradient of epsilon dot product E vector plus epsilon divergence of E, and that means divergence of E is equal to, if I replace epsilon with, this is epsilon, so epsilon is replaced with epsilon 0 times n square. So let's say, so divergence of E over here is 1 over epsilon times gradient of epsilon dot product E. So divergence E is equal to 1 over n square gradient of n square dot E. And the right. And curl of E can be rewritten with the vector identity like this: gradient of divergence E minus del square E, and gradient of divergence E. So this is a divergence E is given over here. So this is gradient of 1 over n square del n square dot E minus del square E. And we can ignore this one when the refractive index change is very small. So gradient of this one can be approximated to be 0 when refractive index n varies slowly, or the difference between the two medium, refractive index difference between two medium is small. Then we can approximate that as just the del square E. Then with that condition, we can convert this vector wave equation with the scalar wave equation, that is del square E minus C n square over C square round square E over round T square. This is the scalar wave equation. 전자기하에서 여기까지는 했죠?
네.
오케이. 그럼 됐네. 자, any question up to this point? The condition is like this. If you have a two-medium boundary, we studied the Fresnel equation, reflectivity and the transmittivity of the electromagnetic wave at the boundary. We have already covered that one. And that is the vector equation. We consider two cases, TE wave and TM wave. Right? So we apply the continuity condition for the D normal and the continuity equation for the B parallel. So that reflectivity and the transmittivity equation obtained from the Fresnel equation is the vector equation, but we like to consider a scalar wave transmission or reflection from the boundary. That means it's identical. Vector wave and the scalar wave becomes identical. The TM or TE waves becomes identical when incident angle theta is very large. So it is very different near the near the critical angle, but if it is near the 90 degrees, its two equations becomes almost identical, and that's the condition. And we have a scalar wave equation in this case when the refractive index difference is small. So let's say, how can we find the scalar wave equation? The process is quite standard. And the first thing you have to do is we decompose the spatial and temporal dependent function of E with the product of spatial function with a temporal function. And then we apply separation of variables. And if we assume this one and put it into equation 7, and then we divide both sides with the E, then we have, if we take this one to the right side, then we have ET and del square ES plus constant ES times the second order derivative with the temporal function of E. And if we divide both sides with this, then we have left side only a spatial function, right side is only temporal function. The only possibility we can have is to assume this as a constant. And we assume this is a, in Schrödinger equation, we assume this is a constant E, right? The energy, the eigenvalues or the energy level of electron. Here, we assume this is a constant, but that is omega square over c square to simplify, to cancel out c square. Then we have two equations. Second order derivative of E as a function of t, temporal function of t becomes constant times itself. And the second order derivative of E as a function of spatial coordinate becomes another constant in itself. So these are just a equation 8. Over here, equation 9 is not a constant. N is the function with respect to a position. So 8 B is a constant. So equation 8 has a simple harmonic solution. So we assume that the temporal equation becomes the A times exponential minus plus I omega t plus another constant times I omega t, exponential minus I omega t. And the equation 9 is second derivative of space is a function with respect to space times itself. And right. And we consider a waveguide whose refractive index only depends on x and y. Then we can put this one over here, and the del square can be written as the second order derivative with respect to x and y and z. And we applied another separation of variables because left side is only a operation with respect to position x and y. Right side is the operation with respect to z. So we assume the solution xy, E spatial solution xyz with a transverse solution of xy and the axial solution Ez with respect to z. And if we put this equation 9 again, we and divide both sides with the Es, we have another situation which has only xy dependent on the left side and z dependent on the right side. So again, we can assume this is a constant. And this constant, we take this as k effective square. We can take any constant, but to make a physical meaning, we assume this one is equal to k effective square. And k effective square has a physical meaning, and I'll explain this later. So it's split into two equations, differential equation. First one is second order derivative of Ez becomes k effective square, constant times itself. So this one becomes another sinusoidal function, and the another equation left becomes like this. So we have this del square second order, del square with the two-dimensional space, k0 square n if n of waveguide xy, and t becomes k effective times et. And if you compare this with the two-dimensional Schrödinger equation, if we convert there is to be h square over 2m. If we divide that, then del square psi becomes minus this v, because there is used to be minus h bar square over 2m over here. So we take this to the right side by dividing it. We have this one and this one. So this two-dimensional waveguide equation, this is called two-dimensional waveguide equation, scalar waveguide equation, becomes identical to the two-dimensional Schrödinger equation if we assume that the potential minus potential times constant equals to k0 square n square. And k effective becomes I think be sign correct? Oh, okay. Right, this is correct. Okay, so K effective minus K effective correspond to the energy, and the n square correspond to the minus potential. So if we have a waveguide structure, this is a multimoded graded index waveguide, the fiber, and the step index fiber, and this is single mode step index fiber. And this structure, where the refractive index larger at the core, is like negative potential at the core, because minus n square minus correspond to the potential. So the reason why there is a high refractive index near the guiding area of an optical fiber is because the potential should be negative. So larger refractive index correspond to the negative potential over here. So we can convert that. We can compare these two. And the waveguide equation is to solve this equation. And as you can see that the z dependent of this one is like this. So this one corresponds to the propagation vector of a guided mode within a waveguide. I'll explain this a little bit later. This is a typical example of guided mode for the scalar wave equation. LP01 is the ground state mode. It's like the angular momentum. It's a little bit different. It's like hydrogen atom model. LP01 is the quantum number along the axial direction is 0 and the radial direction is 1. And quantum number for the axial direction 1 and radial direction 1. So we have the one oscillation along the theta or phi. LP21 represent the quantum number along the radial direction 1 and quantum number for the azimuthal direction 2. So we have two zero crossing here. We have two zero crossing here, right? It's like sine wave. So if we have a sine wave along the phi, we have two zero crossings. So that corresponds to LP1 mode. Right? If we have a two quantum number along the phi starts from 0 to 2 pi, and this is pi, so we have 1, 2, 3, 4 zero crossing. So LP21 shows 4 zero crossing white area that correspond to this node. 1, 2, 3, 4. And here, 1, 2, LP11. LP31, of course, we have 3 oscillations within 1, 2, 3. Right. So we have the 1, 2, 3, 4, 5, 6 zero crossing for LP31. LP03, LP01 is along the R direction. We have this kind of shape, and if you have if you take a look at LP31, we have 1, 2, 3, 4, 5, 6 zero crossing, and the center should be 0. It's like the spherical harmonics. If we have a non-zero, the azimuthal quantum number, the center should be 0. And for this one, LP02, right, 02 over here, we have 1 zero crossing. So that corresponds to the case. We have this, so we have the 1 zero crossing over here. We can think about this is zero crossing, so it has 2 zero crossing. That is LP02. And LP03, we have 1, 2 zero crossing, and that corresponds to the R. We have like this. We have 1, 2 zero crossing. Like this. That's the LP03 move. And along the azimuthal direction, there is no oscillation, so it's a uniform along the angle phi. Right. So these are the standard representation of the fiber modes in a fiber. And these are the structures you can. LP22 mode, it looks like this. So does this make sense? Why we have solved this Schrödinger equation many times so far, and we didn't solve this problem yet. But I'll just give you homework for a given structure of refractive index. How many modes there exist, and what is K effective? K effective corresponds to the eigenvalue energy level E. So let's go back to the original. Let's wrap up this result we have obtained so far. It is right. So far, we assume that we have a waveguide structure along the R axis. This is R1, this is refractive index 1 and refractive index 2. It is larger than refractive index 1. And if the radius of this one is 5 microns and the omega is 2 pi times 6 times 10 to the 12 hertz. So this corresponds to F is equal to 6 times 10 to 12. Sorry, 600. So 600. This corresponds to lambda is equal to 500 nanometer. And if the laser wavelength is 500 nanometer, and if we put that laser into a waveguide whose radius is 2.5 micron, then refractive index difference is, this is 1.51 and this is 1.50. Then we can calculate how many modes there exist within the structure like this. So it's like potential depth is given, and lambda is like the mass of electron. So mass of electron is given, then how many bounded state exist within this waveguide. So we can solve that problem like this. And if, let's assume that we have solved this one. By solving equation 9 over there, the waveguide equation, we obtained K effective 1 is the forced refractive index. Effective K, that is K0 times N effective. This is the definition, where K0 is 2 pi over lambda. So, and omega over K0 is equal to C over N. Sorry, it's a K0 is just C. K0 is the propagation vector in vacuum, so it should be C. So we have this relation. And K effective, let's say K effective 1 is 1.502 times K0. And K effective 2 is effective 1. So K0 and effective 2, let's assume we have 1.508 K0. Let's say there exist two bounded state solutions. These are the bounded state solution, like the energy level eigenvalue for the Schrödinger equation E. By solving that equation numerically, we obtain, let's say, two energy levels, K effective 1 and K effective 2. And we convert that with the K0 times 1.508 and the other one is 1.502. That is like 1.502 is here, and effective 1. And effective 2 is over here, and effective 2. So it's between these two, K, N1 and N2. It's like when we solve the bounded state, physically meaningful bounded state solution for a step index potential, then energy should be within, if this is V0 and V1, energy level, energy 1 and energy 2 should be between these two energy levels, V1 and V0, right? To have a bounded state, to become a bounded state. It's like N effective, it is defined like this, should be within these two, N1 and N2. So these are very similar, these have very similar relation. Once you obtain numerically K effective square, and we can convert that K effective 1 or 2 or 3 in terms of K0 times constant, and this constant is the N effective 1 or N effective 2, and those N effectives should between these two numbers, N1 and N2. And once this is calculated, we can find out what is the solution. The three-dimensional solution of electric field. Can you remember the three-dimensional equation we started from the beginning of the separation of variables? Electric field is like this. Electric field is electric field as a function of R and T is electric field along the X and Y times electric field along the Z and electric field along T. And this is just the exponential I omega T, A times, let's say minus omega T plus B times exponential minus I omega T. And let's say just solution is A times exponential I omega T. So A is constant, so we just ignore this one and we just assume this is exponential, not A, the B times like this is minus I omega T. Let's say this is the solution of our choice. And electric field along the Z direction is, what is this? K effective. Right. The solution of this one is, instead of writing this, let's just say this is A times. So let's write this total A times exponential I omega T plus B times exponential minus I omega T. And this is C times exponential minus I K effective times Z. Plus C times exponential I K effective times Z plus B times like this. And here we have the solution E, X, and Y. So once this is given, with this, the electric field as a function of transverse direction is like this. Once this is given, or this is given, electric field along the XY coordinate intensity is given one of them, then that does not change with respect to time or with respect to Z. So intensity profile along the cross section does not change as it propagates along the Z direction or time direction. So if this is a waveguide, and this is Z axis here, and XY axis, X and Y axis is here. So along the XY direction profile, it does not change, but it propagates for a wave propagating along this one. It is combination exponential I k effective times Z minus omega t. And another wave propagating along the other direction is the combination of exponential I k Z effective times Z plus omega t. So this is the wave propagating along negative Z direction, and this is the wave propagating along the positive E direction. And for either case, its intensity profile is just constant, regardless of the propagation direction Z or T. So this is the final solution we obtained. And the intensity plot over there just plots the electric field along the X and Y direction. So these are the solutions of electromagnetic wave. As it is given here, this one defines for a given mode, E1, that is one of ELP01, LP01 mode profile is given, then N effective is one of the, N effective is one of them, right? So the N effective is given with the profile of the mode, right? If we have this energy level, like the case for the Schrödinger equation, its profile is determined by this one, right? Its profile is determined N effective. So if N effective is given, N effective LP01, this is a number calculated from two-dimensional waveguide equation. For a given number, this is given. So Schrödinger equation is like this. We solve a lot of different modes for hydrogen atom, but they have time-dependent variation, right? So each mode evolved with different temporal oscillation period. So that normally people do not consider time-dependent function in Schrödinger equation, but each bounded state mode of Schrödinger equation, they have different time-dependent evolving constant, omega. So they evolve with a different time constant, and these are the given by the spatial solution of Schrödinger equation. It's like the two-dimensional waveguide. N effective is given by the spatial profile. And for a given profile, N effective is different, so that means the phase velocity of, for a given mode, V phase LP01 mode is C over N effective LP01 mode. So for a given mode of N effective, the phase velocity is determined by that. So that's the situation we have. That's the physical meaning. And these are the different types of refractive index for for different optical fiber. This is step index optical fiber. This is depressed cladding optical fiber. And this is double core optical. Right, so this is another deep, anyway. And the triangular shape of structure, or triangular core plus depressed cladding, all of these structures are patented. And right, these are the dispersion flattened, dispersion shifted fibers. They are all patented depending on its structure. And when we used to, with 4 professors, when I was in GIST, 4 professors combined together to have a project with Samsung Electronics. Samsung Electronics at the time has a optical fiber manufacturing facilities in Kumi area. And the mission was to design a dispersion shifted fiber, dispersion flattened fiber, and avoiding the previous the patent. So it's designing a waveguide structure to have a different dispersion property of an optical fiber. Can you remember when we do the pulse propagation, if this is a wavelength, the refractive index, the dispersion is like this. This is dispersion 0 point, and 1300 nanometer, near the 1300 nanometer, we have dispersion 0 point for a diffused silica glass. And people like to have a fiber, it has dispersion 0 point at 1550 nanometer. So we like to shift this one, dispersion like this. And that's how people do dispersion shifted fiber, by having a triangular shape. People can shift this one 0 point to 1550. The reason why we need to have a dispersion 0 at 1550 is there is an amplifier at 1550 nanometer. So Obium dot fiber amplifier was developed around that time, and it is by making a different structure of optical fiber. And this is a typical example we can solve with the finite difference method. If the refractive index structure is like this, this is SiO2 has 1.44 refractive index, and here is a silicon. It has 3.4 refractive index. Then we have a guided mode near the structure, and these are the 2 guided modes reported in a paper at 2002. And how can we solve these intensity profile? These are solved by the FDM. And as I explained previously, there is no total internal reflection boundary over here, but still photons are bounded near here. So it's like if we have a potential well for an electron, if we have a potential, low potential over here and high potential over here, electrons cannot escape from this structure, even though there is a tunnel along the x direction. Electrons cannot escape this potential well for a bounded state given between these two potential. So the only thing we can explain how photons or electrons can be bounded with this kind of structure is by solving two-dimensional Schrödinger or waveguide equation by using the finite difference method. These are people make this kind of waveguide with the semiconductor lithographic technique, and people like to make a single mode because if there exists multi-mode, each mode have a different phase velocity and different group velocity. So if you put a single pulse, it's split into 2 or 3 or even more. So you cannot have a high-speed communication with a multi-mode waveguide. Right, that's about the content. I'll give a homework to solve waveguide N effective for a waveguide. It looks like this. And then we'll have 1 week break, and we'll have a final exam 1 week after Monday. 자, 여기까지가 수업 종강하겠습니다. 여러분들 뭐 한 학기 동안 수고했고, 여기 안 나온 부분이 되게 많죠. 교과서에도 없고, 왜냐면 다 논문에 있는 부분이기 때문에 교과서에도 없고, 뭐 어디 찾아봐도 잘 없죠, 그죠? 그래서 이런 부분이 여러분들이 그 윈도우가 지금 2000인가요? 지금 윈도우 버전이 몇이에요?
그냥 윈도우 11로
11로 했구나. 윈도우 2000 나오고 뭐 11 나오고 10 나오고 그러잖아요. 그러면 윈도우 10에 대한 그 매뉴얼 북이 도서관 가면 한 1000페이지짜리가 한 3권 있죠. 그런 거 본 적 있어요? 윈도우 매뉴얼이 그렇게 있어요. 그거 다 읽어야 윈도우 사용하는 거 아니죠. 그냥 쓰면 되죠. 그죠? 그리고 필요한 거가 있으면 거기 좀 찾아보면 되긴 하지만 뭐 인터넷 찾아보면 더 빠르긴 하죠. 여러분들이 지금까지 1900년대 그 맥스웰 이퀘이션 배우고 슈레딩거 이퀘이션이 1930년대까지 하고, 그럼 나머지 거 어떻게 커버하겠어요? 지금까지 2020년까지 다 배울 필요가 없어요. 2단계에서 여러분들이 4학년만 졸업하면 바로 리서치 단계로 바로 들어가면 됩니다. 아까 얘기한 그 매뉴얼 다 읽어봐야 윈도우 사용하는 게 아니에요. 그냥 여러분들이 쓰는 윈도우는 다 알고 있는 윈도우예요. 그죠? 그 중에서 특별히 여러분들이 뭐 어떤 펑션을 쓰고 싶다 그러면 찾아보면 되지만 리서치 똑같습니다. 여러분들이 뉴턴 시대 1600년서부터 2020년대까지 다 배워야 리서치를 시작할 수 있는 게 아니에요. 여러분 다 배웠다고 생각해야 돼요. 지금까지. 내가 오늘 이번 코스에서 가르친 건 다 2000년대나 1990년대, 2000년대, 2010년대 내용이에요. 모를 게 없잖아요, 여러분들 사실. 그죠? 테일러 익스펜션만 알면 되는 수준이란 말이에요. 그죠? 그러니까 다 알 필요가 없어요. 리서치를 다 알고 시작하면 늦습니다. 지금 시작하면 되고, 지난번에 얘기한 것처럼 인턴들 많이 하고, 우리 실험실에도, 우리 실험실은 난 늙어서 잘 못 가르쳐요, 여러분들. 그래서 과학 특별히 박사과정 하고 싶다 그러면 내가 카이스트에 잘 아는 교수 있거든요. 진짜 잘해. 내가 소개시켜 줄 수 있어요. 그 사람이 나한테 인턴 좀 없냐고 부탁도 하고 그랬거든요. 그래서 카이스트에 가서 한 2달 정도 하고 괜찮으면 거기 대학원에 가도 좋고, 그렇습니다. 과학이 굉장히 재밌고 아이디어가 전쟁이에요. 내가 노벨상 그거 받은 거, 최근에 받은 거 내가 얘기를 시간이 없어 못했는데, 진짜 브릴리언트한 아이디어가 있다? 그럼 과학을 하면 됩니다. 자, 수고들 많았습니다. 뭐 나한테 연락하고 싶으면 이메일로 하세요. 네, 수고했어요. 네.